Welcome to the second lecture of our course PWM rectifiers, and we are going to talk about the diode rectifier circuits with C and LC filter. Okay, and can be seen in the course structure and the content. We are in module A and we are going to cover these diode and thyristor rectifiers. Now, in the earlier lecture, that is in lecture 1, we have seen the diode rectifiers feeding a DC motor. Okay, so where we had seen that our motor was represented by a constant current load. Okay, so the motor was behaving like that. But in this lecture, we will take up another application where the load is something like a capacitive load with a resistance, which is basically used for making a DC voltage source. Okay, and this is what we will analyze. So instead of a constant current load, we will see how the converter or the diode rectifier behaves when there is a capacitive load at the output. Okay, although this circuit is possible, the circuit here with a simple diode rectifier and a resistive load here, it is possible, but we will not use this circuit because this is not very popular, and a full bridge version of this circuit will be used. So basically, what is the idea here is that if you put a capacitor instead of an inductor, what happens is that the diode, as you have seen, it is when the AC voltage is more than the capacitor voltage, the diode will conduct here. Okay, and then this diode ideally is a short circuit, and considering that there is an ideal diode, and so the circuit will look like here, what is shown. And the diode will stop conducting when the AC voltage is falling and is less than the capacitor voltage. Okay, and then the diode will get reverse bias and it will no longer conduct, and therefore the capacitor will now discharge through the load resistance, right? So this kind of a charge and discharge. So during this time here, the capacitor is charging up, and in this condition the capacitor is discharging. Okay, this is the basic concept: charge discharge through the load resistance and the AC supply. Okay, now full bridge version is a more popular choice. Okay, where we want to produce a DC output voltage. So this is basically the AC input here. Okay, and we have here the DC output voltage. Okay, so this is very popular. I mean, for any kind of like low powered, low voltage DC output, we usually use this kind of a circuit. It is cheap, very easily can be done, and but it has some problem, okay, which we will discuss, and we will find out what are the problems with this circuit. So how does this circuit operate? Very simple. So there are, again, like previously, we can analyze the circuit in two halves, the positive half and the negative half of the AC cycle. And in the positive half, what happens is that, so if we take this, so this is the positive half of the AC cycle, and during this period T1, okay, the capacitor, so the output voltage is like this. Okay, the capacitor is charging like this, and it is like this. So this part of the AC voltage comes across the load because the two diodes D1 and D4 are conducting. Okay, so during this point D1 and D4 are conducting, right? So therefore the the I0, the load current waveform is something like this, which is following the V0 voltage because we have a resistive load like this. And during this portion, the current is taken from the source, and therefore this current is something like this. Okay, now this is the source current which is flowing. Now after this point, like during this point T2, right, what happens is that the AC voltage, that is this part of the voltage, this AC voltage here, is basically less than the output voltage. Okay, this is the voltage at the output at this point at the beginning of T2, and the AC voltage is less than V0. So when that AC voltage becomes less than V0, then the diode stops conducting. So the diodes, these two, stops conducting, and therefore the capacitor actually starts to discharge through this length. So this is what is shown here. The capacitor is discharging here in this way. Okay, and all the diodes, all these diodes, these 4 diodes have stopped conduction during this time. And since the diodes have stopped conduction, what will happen is that the capacitor voltage will now fall with an RC time constant. Okay, so basically it will exponentially fall. So this is basically part of this exponential falling, but we can take a small part. If the RC time constant is very large, we can take a small part of it, and so we can see up to this point, okay, in the waveform. Okay, of course, since all diodes have stopped conduction, we don't have any current flowing from the source during this point of time, and I0 current is something like this, which is fun. Okay, now at the start of the so this will continue until the voltage again. So now in the negative half of the AC cycle, again the rectified voltage waveform is something like this. Okay, so it will again hit here, where the AC voltage, instantaneous AC voltage, will become more than the V0 voltage, and therefore again the diodes will start to conduct, but now the diodes D2 and D3 will conduct here, and again it will follow, and then this will follow like this. Okay, and here therefore the current is something like this. Okay, so the in this way, what we see here is that this is the output voltage waveform, which will have a ripple, okay, and a DC component here. Okay, so this is the DC component, and there is a ripple on the output voltage. So basically, which means that we are able to produce a unidirectional voltage or a DC output at the DC voltage output at the output of this converter. Okay, yeah, so the negative half cycle is given that the diodes D2 and D3 will get forward bias and turn on. So here again what will happen is during this point, right, D2 and D3 will start to conduct, and the process will repeat. So here D1 and D2 will conduct, and the other portion D1 and D4 will conduct here, and D2 and D3 will conduct in the other portion. Okay, this is how it goes on, and we can get such a output voltage waveform at the output of the converter. So we and this is shown here. Okay, you can see here the output voltage, and we can actually find out mathematically how much is the peak to peak ripple voltage on the output. We can find out mathematically. So so this is the output voltage full bridge circuit waveform, whose waveforms are given here, and here let us assume that this T1 is the charging time of the capacitor, and T2 is the discharging time of the capacitor here. Okay, so during the time T1, C will charge to Vm if AC input voltage is Vm sin omega t. So as you can understand, during this portion, even this portion, so during this portion here, the capacitor voltage is following the AC input voltage, and from T1 to T2 what happens is, so this voltage, so this point is V max, okay, Vm, after which the AC voltage starts to fall, and therefore the capacitor is disconnected from the diode bridge rectifier or from the input side, and it starts to discharge. So we can say that the output current here is Vm by R e to the power minus T by RC. It is falling in with an RC time constant. So this is the RC, it will fall with a RC time constant tau. Okay, so therefore this output voltage will have a this, so this equation here for this voltage will be Vm into e to the power minus T by tau. Okay, so with this it will start to fall. So therefore we have now found out that the peak to peak ripple voltage, how much will be the peak to peak ripple voltage? It will be, this is the Vm voltage. So at this point the voltage is Vm, so this is a Vm voltage, and at the end of T2 the this voltage here is Vm into e to the power minus T2 by RC. Okay, this is the voltage at this point. So therefore we know what is the peak to peak ripple voltage on the output, right? So here we have also shown that the VR peak to peak ripple voltage, so this is the V0, this is the V0 voltage output, okay, which has this VR peak to peak, and there is a DC component here. Okay, so there is a DC component and a ripple component. This scale here is very large. Okay, the ripple voltage here is very large here. Usually this voltage may be this, say we have this 100 volt here, the average voltage, and this ripple can be only 1 volt. This is very practical, 1% ripple or 2% ripple. Okay, so this scale is exaggerated. Scale is exaggerated. It generally looks like this. Okay, so generally you will hardly notice a small ripple on a voltage. So this voltage will be 100 volt, and you may have a peak to peak ripple of say 1 or 2 volts. Okay, you will hardly see very small ripple on the output voltage. Okay, so anyway, so if we can further actually simplify this peak to peak ripple by saying that if the RC time constant is very large, so we can expand, say that e to the power minus T2 by, so we expand the e to the power x, that we can do an expansion of that factor, and so we will take only the first term, the second terms being neglected. Okay, the 1 minus x plus x square by 2, and those the second order terms are neglected, and so we get only the 1 minus e to the power minus T2 by RC can be written as 1 minus T2 by RC, and therefore this VR peak to peak, substituting back into the equation, is something like this, which will come out to be Vm into T2 by RC. Okay, now again, since RC value is very large, okay, we have a very large time constant of this R and C, right, which is very practical. This happens generally. Then basically T2 is much more than T1. Okay, the T1 portion is very, very small as compared to T2. Okay, T1 is a very small fraction. So therefore we can say that T2 is almost covering the whole of the half the time period. Okay, so which means that basically the voltage here, if you see, the T1 portion is very small and T2 is very large. Okay, so this is like T1 here, and this is T2, and then very, very small T1 and very large T2 like this. Okay, this is more practical if the RC time constant is very large. So we say that T2 is almost covering the T2 is almost equal to T by 2 here. Most of the period is T2 only, and so we can make that approximation, and VR peak to peak is Vm by 2f RC, coming from this this equation here. Okay, so therefore V0 average voltage is Vm minus VR peak to peak. So this is the Vm and this is the VR peak to peak divided by 2, and that is this voltage V0 DC. Okay, this is the V0 DC voltage. We will take up an example on how to find out these voltages sometime later. One of the yeah, so therefore here we can see that the capacitor here behaves as a C filter, allowing the AC ripple to pass through it. Okay, so the DC cannot pass through the capacitor because the capacitor has infinite impedance at DC. So the AC component will pass through the capacitor and the DC part will go through the load. Okay, and we can also understand that the ripple will reduce if this RC time constant is large. Okay, the ripple will go on reducing. So if RC is large, VR peak to peak will go on reducing. So if C is large, basically if the capacitor is large, then peak to peak ripple goes down, right? But what will happen is, if you see carefully, the input current becomes highly non-sinusoidal, right? Why is it so? Because here you can see that the input current, okay, this input current here will become highly non-sinusoidal. Okay, so if T1 becomes very small as compared to T2, then what will happen is like this, and it's like this. Okay, so the input current input current if T2 is like this, and it can be like this also, very sharp into. So this is a big problem. If you increase the value of the RC time constant, or if you increase the value of the capacitance, basically the input current will become, because the T1 will become smaller and smaller, and the input current will become more and more peaky in nature, very sharp rise. What is the reason for that? Because anyway, if you understand here, is that this capacitor, okay, or the capacitor at steady state has a constant voltage, which means that whatever is the energy coming into the capacitor over this T or over a fundamental cycle, that energy must go to the load. Okay, so in order to maintain a stable capacitor voltage, so which means that if it is discharging for a long duration, it must charge, and it is charging in a very short duration of time, it means that it must take the energy within that short period of time. So that is why the input current is becoming very peaky in nature, because it is trying to extract that energy which is required by it, so it becomes very peaky. It is drawing a lot of energy during a small T1 period, which it will deliver to the load during a bigger T2 time period. Okay, a short intake but a large or long output time duration for the capacitor. Okay, and during that short period, because it is taking a lot of energy, the current must go high. So therefore the source current is very peaky. This is a very big problem with such kind of rectifiers, because the input current is highly non-sinusoidal. So that is what I have said here. The input current is becoming highly non-sinusoidal. This is a very big problem. Yeah, the source current waveform profile is highly peaky and non-sinusoidal. Okay, so this is the source current waveform, which becomes very, very peaky. So a large capacitor at the DC side distorts the source current and results in poor power factor, and many utilities will not allow this. So if you are taking like a very small amount of power, say 5 watt or 10 watt from the grid does not care about it. But if you are drawing huge amounts of power, say kilowatt, with such non-sinusoidal highly peaky current, actually it is very detrimental to the grid operation. Okay, the grid has many problems that it will face, okay, when you draw such high peaky current. And so there are regulations. For example, there is IEEE regulation where it says that the current cannot be so much non-sinusoidal. So there is something called as THD, total harmonic distortion, which we will cover in sometime later in the course. So we will have, so this is a solution. Diode bridge rectifier with capacitor load is a solution, but it is not a very good solution in terms of the input side power quality, which we have to improve as part of the PWM rectifiers. Now, instead of this C filter, okay, it is also possible that we can use a LC filter at the output. This actually improves the performance. Okay, what happens with an LC filter is, you can see here, an LC filter means you have an L and C, okay, connected like this fashion. Okay, so what it does is that, so if you see the output voltage of the bridge rectifier, it is a rectified AC waveform which is like this way. So this is the output voltage of the rectifier, and if you do the harmonic analysis, of course it has some DC component which is here, but it has all the second harmonic components, like it has 100 hertz, 200 hertz, 300 hertz, like this. All the components are present, okay, at the output of this voltage. Okay, if you do the harmonic spectrum of this, so LC filter, okay, can be very good where it can actually attenuate these higher order harmonics. So what is our aim? Remember that our aim is that we want all the harmonics to go here, okay, and all the DC component should go here. Okay, that is what is our aim, right? So we have put a filter here. So this is the V in voltage, right? And here is the V out voltage, V out. So we want that the V0 is a perfect DC kind of thing. Okay, so all the harmonics should go through the LC filter. Okay, but now if you see the LC filter, you can see the output, the voltage gain of the filter, and you can see this is typically, you can just put the transfer function of this one, and you will find that it has a transfer function like this, right? So the gain is 1 at DC, because at S equal to 0 the gain is DC, so the gain is fine. At DC you get the input voltage equal to output voltage, that is good. But then it and then it rolls off at minus 40 dB per decade after the cutoff frequency, because there are two passive elements, LC, and because of this factor here, it rolls off at minus 40 dB per decade. Okay, so therefore this LC filter is a low pass filter, because at DC it has a gain of 1, and then the gain starts to fall, which is good because it attenuates the higher harmonics. Okay, all the 100 hertz, 200 hertz, all these even harmonics, that will be attenuated by the LC filter. That is good. Okay, so we can actually determine how are the values of L and C. So this is a slightly advanced thing, but we will just cover it because this course is a combination of UG and PG content. Okay, so how will you determine the values of L and C? How can you design the output value? So the output voltage of this diode bridge rectifier, if you can do the Fourier series expansion, I will not do it here, and I will leave it to you as an exercise. You can see any book, you can do the Fourier analysis of this waveform, and you will find that all of these harmonics, all the even harmonics will come in the output. Okay, this is the DC component, and there are all these even harmonics coming at the output. Okay, what do we want? We want that the DC should be fed to the load and all higher harmonics should be attenuated. Okay, ideally all these 2 omega, 4 omega, 6 omega, these harmonics should be completely attenuated. It may not be possible to fully attenuate everything, but first, because the second harmonic is the most dominant, the fourth harmonic is actually, you can see here, is 1/5 of the second harmonic, right? So if we target the second harmonic, right, we find that it is the most dominant, and we should design our filter in such a way that the second harmonic is attenuated, right? So yeah, so for any harmonic, okay, you can understand here the L acts as a high impedance. So any harmonic current is coming here, the L is the omega L, so this L is acting as a high impedance, and this capacitor is 1 by omega C, so it acts as a low impedance path. So any harmonic will first see a high impedance in the L, but some of the part will come up to this point, and then it sees a low impedance, so the current will pass through, the harmonic current will pass through the capacitor. So this is the basic idea of this one. Okay, now so obviously we can say here that this capacitor, the impedance of this capacitor, which is 1 by n omega C for the nth harmonic, okay, the impedance of this capacitor is 1 by n omega C, right, where n is the order of the harmonic. That impedance should be much less than this Z, okay, because what we want at the nth harmonic, which can be second harmonic, it can be fourth harmonic or sixth harmonic, we want that all the harmonic current should pass through this capacitor, nothing should pass through the load. So this is the load here, okay. So we want that the Z of the load, okay, the Z should be much greater as compared to the capacitive impedance, okay, for all the harmonics to pass through the capacitor. Okay, this is what we want. So we have to design in such a way, so this is a good choice, right? So this is a good choice, that the Z or the load impedance is like more than 10 times the impedance of the capacitor. Okay, so this is a good choice here. Okay, so if this is satisfied, then the load impedance Z can be neglected. Further analysis which we will take up in the next slide. So this is one condition which can be used to design the values of L and C. So when this condition is satisfied, right, then we can say that this IN, okay, IN is this current here, okay, IN, assuming that the Z does not exist, so Z is very large, so Z is very large, so therefore IN is equal to, so Vin is this voltage divided by n omega L minus 1 by n omega C. Okay, yeah, so this is the absolute magnitude wise. Okay, so this is the current which is flowing in here, and the nth harmonic voltage appearing across C is therefore, so this current, if I assume that the entire current is flowing through the capacitor, so IN into 1 by n omega C, right, is the voltage across the capacitor, which will be something like this, right? Fine. So this for example, if you take the second harmonic component, okay, if you consider that you are designing the LC capacitor, LC components based on the second harmonic, so therefore the VC2, that is, what is VC2? The second harmonic component of the capacitor voltage is Vin2. Vin2 means the second harmonic component in the input voltage. So Vin2 divided by 2 omega whole square LC minus 1, coming from the previous equation. Okay, this is this equation. From this equation, the next equation comes by putting n equal to 2, right? N equal to 2. We have put n equal to 2 here. So therefore, what happens is V in 2 is 1 by root 2. So from the Fourier expansion, we have already found out what is V in 2, right? We have found out what is V in 2. If you see here, this is V in 2. Okay, this is the second harmonic voltage here. Okay, so we can put it here, 1 by root 2 into 4 Vm by 3 pi from the Fourier expansion. So there is one term. So this is the VC2. This is the capacitor voltage, second harmonic component of the capacitor voltage. Okay. Now there is something called as a voltage ripple factor, VRF. Okay, and VRF is VC2 divided by VDC. What does it mean? It means how much is this second harmonic component. Okay, how much is the second harmonic component here on the output side, how much is the second harmonic divided by the average. Okay, so this is the average voltage and this is the second harmonic contribution. Okay, so basically this we are quantifying with the help of a voltage ripple factor, VRF. right? So the DC part is 2 Vm by pi. This also comes from the Fourier expansion, if you Fourier series expansion from the previous one. And Vc2, we have just found out Vc2 comes from here. Okay, Vc2 is coming from here, and therefore if you simplify this, we get this equation. Okay, so using 1 and 2, 1 is here, 1 is this equation, and 2, which we have already said, we can say that we can design the values of L and C, right? So yeah, we will it is possible to use the use these equations. Now let us take a simple example for a diode bridge rectifier with a C filter, okay, with a transformer. Suppose this is a very practical application. We often, as I told you, we want to, what is the main idea of this one is that suppose very often we want to create a 15-volt supply. Okay, so this is like this 15-volt supply we are trying to make from a 230-volt source, AC source, 230-volt, and we want to make here a 15-volt DC supply, and the power level is also small, okay, 10 watt of power sense. So that this power is 10 watt, which is taken by the load. Many cases this kind of small applications, this kind of rectifiers are very frequently used, okay, because the power level is small. This is a very cheap solution, okay, very readily used. So what we can do here is that we can actually use a transformer. Okay, in many cases the transformer helps in isolation, which is needed in many cases. We have a transformer and we have a diode bridge rectifier here and a capacitive filter. Okay, we can design the values of the C and we can find out how much is the peak to peak ripple on the output voltage. Okay, so what is the peak of the AC voltage? So the peak of the AC voltage is Vm, and suppose this is 230 volt RMS, so which means 324 volt is the peak AC voltage, right? Now suppose, let us assume a 21:1 ideal transformer. Why this value will come, you will see very quick soon. Okay, so if you put this 21:1 transformer here, what will happen is the secondary voltage here, Vm secondary, okay, this voltage will be 324 by 21, about 15.44 volt, right? What is the V0 DC? So the DC voltage output, as we have deduced from one of the equations, see previous equation, if you can recall this previous equation. So Vm secondary minus Vr peak to peak divided by 2, that was the DC output. So this is where the V0 DC comes here, right? So then this is 15.44 and minus 0.025 V0 DC. Why is it 0.05? We have said that the output ripple is less than 5% of the average output voltage, right? So this Vr peak to peak is 5% of VDC. So this is 0.05 V0 DC. Okay, so therefore V0 DC is something like this, where therefore we can find out that V0 DC is 15.06 volt. Okay, so which is approximately very close to 15 volt. So this is what we have targeted. That is why we had actually taken a 21:1 transformer. Okay, you can see here that this is 15 volt, about this one. Okay, now therefore we have also said that the power is going to be like 10 watt, about 10 watt. So therefore the resistance or the load resistance is about 22 ohm. So this is the R here, and is equal to about 22.6 ohm. Okay, fine, because this is the voltage divided by the power here. So Vr peak to peak now will be equal to 0.753, which you can find out from this equation. We say that Vr peak to peak is 0.753, and you can recall that we had said that the Vr peak to peak is Vm secondary divided by 2 FRC. Okay, from this equation we can see what is the value of the C. Okay, 9.1 millifarad. That much of C we have to use. Now this example which I have shown here is a very crude example. Okay, there are many non-idealities which we have not considered. Okay, the transformer again will have is non-ideal. Okay, the transformer, I have taken an ideal transformer. It will have a series voltage drop, right? So rectifiers will have additional drop in presence of transformer source inductance. So the transformer source inductance causes the output voltage to fall, okay, a little bit. Device, the diodes are not ideal, so diodes have a device drop. Okay, so if you consider all these non-idealities, it may be useful. Instead of 21:1, you can have a 20:1 transformer to take care of this drop. But again, the problem with this approach is, what is the advantage of this approach? It is very cheap, readily available, so everyone can make a 15-volt power supply very quickly. Okay, now nothing is there. In fact, if you see the circuit, this is very simple. A transformer which you can readily buy in the market, diode bridge rectifiers readily available, capacitors readily available, and you can connect, so you can make your 15-volt power supply. The problem is, or the challenge of this approach is, that if there is any fluctuation in the input AC voltage, there is no way the output voltage is not at all controlled. It is totally uncontrolled. Okay, so it's a crude power supply, but it will work. Okay, so the output voltage, so that is one problem. The other problem is that, so you cannot adjust the output voltage. Okay, so if there is input voltage fluctuation, you cannot change the output voltage so that the nice stable output voltage is possible. So that is not possible. The other problem is that this current is also highly non-sinusoidal, which, okay, if it is 10 watt, fine, so very less power, it can be kind of like acceptable to the grid. But if the power level is going up, then we cannot do that. Okay, so then we have to go for some other alternate arrangements, like a rectifier, PWM rectifier, some form of a converter at the front end. Okay, to improve this current. So we are now taking a very simple practical application where we want to make an LED, okay, LED power supply from this diode bridge rectifiers. Okay, and this is very much used. LED bulbs require commonly converted from AC power from our home outlets, which we use in our home. Okay, so this is a very simple one, and the LED load requires 2 volt and 5 ampere. Here the voltage should be 2 volt. Okay, 1 ampere. The source Vs is supplying 230 volt 50 hertz. Okay, now we have used a capacitor filter and a voltage divider with R1 and R2, right? So this will and then there is a Zener diode. Zener diode prevents any sudden voltage overshoot to the LED. Okay, so we can here find out what are the values of capacitance required if the output voltage ripple is restricted to 2%. Okay, so here the output voltage is restricted to 0.02 of the here. So in order to solve this circuit, we see that so we have this circuit here, and we have the capacitor which is filtering out the output voltage ripple. Okay, and so at first we will find out what is the average output voltage. So V0 average is coming here. Okay, and we have already derived the expression for V0 average, which is shown here. And if we put these values, so we have like Vm is √3 into 230. 230 volt is the RMS value of the incoming AC. And we have also assumed in the example that we have a 2% ripple on the average output voltage. So if we put these values into this expression, we say that V0 average is 321.78 volt, which we can take it as 321 volt. Okay, so this is the first part. Now we have to design or find out the values of these two resistors, R1 and R2. In order to find that values, we will first assume that the voltage at this point, this is the voltage which is termed as Vx. Okay, So this Vx, once we assume it, so we can apply the KCL equation into this Vx, which is like this point voltage is around 321. So 321 divided by Vx minus Vx by R1. So this is the current flowing, and which will be the current flowing, sum of the current flowing which is going through these two parallel paths. Of course, the Zener diode is for protection purpose only, and we have assumed that the Zener diode is not broken, so no current is flowing through the Zener diode. Okay, so therefore we get this expression here. Now we have assumed that this LED circuit or the LED driver which is working is taking a current of 1 ampere, which has been already mentioned in the problem statement, and also it is said that we would like to maintain a voltage of 2 volt across this Zener diode. So therefore Vx is equal to 2 volt. So if you now assume that this R1 is equal to 300 ohm, okay, we have just make an assumption and put this R1 into this equation, we will get a value of R2 equal to 30.3 ohms. Okay, so we get the values of R1 and R2. Some other values are also possible, but we have to satisfy these equation. Now next part is the value of C. Okay, how or what can be the value of C? So in order to find out that value of C, we can use this expression of peak to peak ripple. Again, this expression we have derived it before in the previous slides, and so therefore if I put these values here, C and like this, and put the Vm value, and the frequency is 50 Hertz, and R is total R is to 330, and this is the peak to peak ripple. The value of C comes out to be 1.53 millifarad. Okay, so this is one way of kind of designing the designing this circuit and make it operate. This diode bridge rectifier based circuits are sometimes used, and sometimes other types of circuits, because this is very cost sensitive circuit, because for a bulk of applications the cost is a major factor for these LED drivers. It's a low cost device, so we have to be taking other types of components which are less costly, and so therefore people have come up with other solutions like capacitive divider or something like that, which are also used commercially and quite popular and very cheap. But we have shown you one way of making this kind of a DC voltage source, stiff DC voltage source, which can provide you with some amount of driving current. So thank you very much for your attention. So we now end that lecture 2.